So let's talk first about conservative forces and why they are in fact conservative. So we're going to start with conservative forces. And so my assumption with a conservative force is that conservative forces can create potential energy. That's my assumption, is that a conservative force can create potential energy. So we're going to start by looking at the potential energy piece first, and then explain why other forces cannot create that potential energy. All right? So I'm going to give us a scenario. I have two objects, particle A and particle B. So these are both particles. My current system, we'll call this system number 1, only includes these two particles. So there's no earth in it. There's nothing else in it. These two particles exist. Those are my system. I don't know anything else about them. Now, what I do know about these two particles is for some reason that I have no idea about, that is not incorporated as part of the system, for some reason, these two objects start far apart from each other, and they are going to be attracted to each other, and they are going to get closer together. They're going to move, they're going to speed up as they do it, and they're going to eventually collide and combust. Okay, but these two objects start at rest and then speed up and head towards each other. Why, I don't know, because my system is just these two particles and I can't see anything outside of that system. So why is not a question for me. I just know that that's actually what happens. So if I talk about the energy in my system, my energy in this system number 1, what's the only type of energy this system can have? It's just two particles. There's no earth. There's no spring. So what's the only type of energy it could have? Kinetic. What happens to the kinetic energy of the system? Does it increase, decrease, or stay the same? It increases, right? They go from not moving to moving, both of them. It doesn't matter that they're moving in opposite directions. That has no effect because 1/2 mv squared. So the fact that one of these is going in the negative and one of them is going in the positive doesn't change kinetic energy. The change in energy of the system must be equal to the change in kinetic energy of this system. So this system, as defined by me, of these two particles, right, changing, that system had a change in energy. Anybody have a question about how that happened? Now, something had to cause that change in kinetic energy, right? If my system is defined only as these two particles, that means that this kinetic energy must be a combination of the work done on A and the work done on B. Okay, some external force. I don't know what it was. Maybe it was an alien. Maybe it was a ghost. Maybe it was a pickaxe. I don't know. I have no idea what the object was. It's Halloween. Maybe it was a witch. I don't know. Not in charge of that. I know an external force did work to these. So what I've just put on here would be the concept of the work energy theorem, right? Work done to an object or a system changes the kinetic energy of the system. This isn't new, but I want us to think about how that works, because now I'm going to change the system. That's all I'm going to do. It turns out that I do actually know what caused them to come together. Okay, it was not a witch or an alien or a ghost. In fact, it was a spring. So these two objects were at two ends of a stretched spring. They were released from rest, and so that's why they are going to come together. In fact, they won't actually collide because the spring's in between them, but that's okay. Really important. Physically, what happens to these two objects absolutely does not change just because I redefine the system. Physically, these two objects started at rest. They're going to increase their velocity as they head towards each other. That is still true, even though I changed the system. So now I'm going to make my system number 2. These particles and the spring. So between the particles and the spring, I want to think about what the change in energy of this second system is. So now that you know that there are two particles on a spring, I'm going to say string so many times, on a spring, and nothing else is touching it. They're far away from any other objects. There's no gravity attached to them. These are in deep, deep space. No other forces acting on them. Could there be any external work done to this system? Could there be any external work done to the system? Is there anything touching these objects? I said no. I said nobody was touching them. Is there any gravitational forces when they're out in deep, deep, deep space? No, absolutely not. So, if there's no external force, there can be no work done to the system. That means the change in energy of system 2 must be equal to how much? Say it louder and prouder. 0. Absolutely. That's exactly right. This is fine. Remember, the physical situation did not change. 2 objects released, heading towards each other, speeding up. That is still what happened. I defined these 2 systems differently, so it's perfectly fine that the change in energy of these 2 systems is different. That's fine. Okay? No external work was done on system number 2, so that means that the change in energy has to be 0. There was still, though, because the physical thing didn't change, a change in kinetic energy. So what this must mean is that since the system's energy didn't change, there must have been a change in another type of energy, let's say potential energy, that counteracted that change in kinetic energy. This is how we get the idea that there must be potential energy in the system. A really great example of this is, let me toss this masking tape. I toss it in the air, it comes back down. I theoretically catch it at the same height, right? The kinetic energy of this system starts with some initial velocity, so high, and then when it gets to the top, it's 0, right? But I was able to then fall back down and come back to the exact same amount of kinetic energy at the end. That means somewhere in there, that energy didn't disappear. It just transformed from kinetic energy into something else. So that's what we're saying happened here. I made a change in kinetic energy that had to have happened from some other energy in my system. So, based on this statement, that means that the change in kinetic energy is equal to negative change in U. That is where our negative sign came from. If I play this track to the end, we said work energy theorem right there at the beginning. A change in kinetic energy must be equal to work. Now, that work, those 2 forces existed before. They exist now. They're just internal to the system. So this change in kinetic energy came from work internal to the system. Internal work to the system. If I slightly change this to just say, I want the change in U over here is equal to negative work internal to the system. Just like last class when we talked about work is equal to what? Force times distance. Force times distance if the force is constant. If it's not constant, then I would get this. I'm going to leave it up in the top corner for us. It might be an integral dr. That equation is almost exactly the same equation as the work integral. There's only one difference, and what is that? The negative sign. A change in potential energy is negative work. I figured that out from right here. A change in potential energy is negative work internally done to the system. Whereas a change in kinetic energy was positive work. Does everybody see that? This is one of those things I want you to get before we go talk about path dependent versus independent. Change in kinetic energy is positive work. Change in potential energy is negative work inside of the system. If you look at the equation sheet, you'll see this next to F. Anybody know what the CF might stand for? FCF. What does that probably stand for? Conservative forces, yeah. So if you're like, what is the CF? I don't know what that is. I'm on the test and I can't figure it out. CF means conservative forces. All right, we're going to talk about this now, but there are only really two conservative forces that we have. What are they? Gravity and spring. Gravity and spring. So let's think about that one step further. Okay, I would only need to use an integral if this force isn't constant. We make an assumption here on Earth called the flat Earth assumption. It's not that Earth is flat. That's not what I'm saying. Please don't walk out of here and tell anybody the Earth is flat. I'll cry. It's not what we say. We say that the Earth is really, really, really big. That's what we're actually saying. We're not saying it's flat. We're saying it's really, 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 really big. So if you go up a mountain and stand at the top of that little baby mountain, relatively, the radius you are from the center of the Earth, this is R, that's this tiny little bit right here that we're going to call R1. We're saying that R1 is way, 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 way less than R. So yes, does the gravitational force change with height? Absolutely. Universal law of gravitation, G m1 m2 over r squared. Absolutely it does. The flat Earth approximation just says this really big, that's really small. So on Earth, all the way up to Mount Everest, we're going to say G is the same. Fg is the same. So that means what's the only possible non-variable force that I could have for a change in potential energy? A spring, right? A spring. The spring force by itself, K delta X, that's not variable. You actually do the integral of that, right? Negative K times delta X, there's a negative in there too. dx, just make that X, is what? 1/2 kx squared. That's on your equation sheet. That one's there. So this would be a normal spring, and it is on the equation sheet. You don't have to do this integral ever, right? It's already on there somewhere. Yeah, US. You really only have to use this if I have a variable spring force. You're like, but wait a second, isn't that a variable spring force? Yes, but we're talking about something else. So that works for any Hookean springs. Most springs are Hookean that we've dealt with, but they're going to make something up. They're going to say that the force is e to the x, because they can. And so you have to integrate it, okay? That's the deal here. Should it be kx? Yes, all the springs you encounter on a daily basis are Hookean. That's the whole point. But could there be a non-variable one? Yeah, absolutely, sure. And it'll have a different equation, and now you get to integrate. How fun. So I'm leaving that up there. One thing before we move on to path dependent versus independent, if I rewrite this slightly and want to get that force, conservative force, which is probably just the spring force, I would have had to take the derivative of both sides, right, to get rid of the integral. So that would be negative du dt. So those are my two equations. Maybe they give me the potential energy and they ask me for the force. Okay, did I put dt? Look at me. It's dr. At the end of class, it's dt. That's my problem. Okay, let's talk about path dependent to understand why conservative forces work the way they do, and then we can move on and be close to done. Try a couple of those problems and move on. Question. If I have a ball that rolls down this frictionless hill versus a ball that rolls down this frictionless hill, whether drawn to scale or not, both of those heights are h. Okay? If it's frictionless, right, which one will have the most kinetic energy when it gets to the bottom? Which one will have the most kinetic energy when it gets to the bottom? You can think about just the object as a system. You can think about the object and the Earth as a system. It doesn't matter which one's going to have the most kinetic energy. It would be the same. Why is it the same? if we don't think about potential energy existing, right? Let's say we're just identifying this ball as a system by itself, right? Because we're trying to understand how can a conservative force make potential energy, but a non-conservative force can't. So if this is just the system of the ball, that means gravity is going to do work to that system, right? Work is equal to a force mg times the distance covered times the cosine of an angle. Because is this distance, let's say this one's 20 meters and this one's 30 meters. mg is definitely the same for both balls, but is the distance cosine theta the same for both balls? Right? That distance cosine theta represents the distance that is in the same direction as mg. So mg is going vertically, right? That d cosine theta represents, if this is theta, it's the angle between the distance that traveled and the direction of the force, right? Cosine of theta. D cosine theta is just going to be h. This one, the angle changes a bunch, but if I add up all of the d cosine thetas for the whole thing, I will get back to h. So the distance covered that's in the same direction as my object, or my force, is the same for both of them. So both of these would get down with the same kinetic energy. Oh, tricky question that they like to ask. Do they get down at the same time? They get down with the same kinetic energy, so they get down going the exact same speed. Right? They get down going the exact same speed. Do they get down at the same time? No. Why? This one has a really short fall, or like it doesn't go, but then it's really steep, and then it goes back up, and then it's really steep again. Would it have the same speed the whole time as that top ball? No, it wouldn't. Would its average speed be the same?
Yes.
Why? Does this one experience constant acceleration?
No.
No, mg sine theta is changing, right? So g sine theta is changing. So it doesn't experience constant acceleration, so I can't guarantee that this is going to have the same average velocity as this one. Even if it did have the same average velocity, this one's traveling further, right? So to cover the same amount of distance in the same amount of time, right? But one distance is actually further. So yes, they have the exact same velocity at the bottom. Yes, they have the same kinetic energy at the bottom. No, they don't exactly get there at the same time. Okay, that's because this is a different length. If you magically made this where they had different inclines but they were the same length, then yes, they would absolutely get there at the same time. So the difference here is in length. That's the difference. Okay, what if I add friction? I'm adding friction to this scenario. They got to the bottom, both of these, with the same amount of kinetic energy. That's really cool. What if I add friction? Would friction do more work in this scenario or in this scenario? Think about how much of the distance covered in either scenario is in line with the force of friction. Force of friction would be going up the hill. So this whole distance of 20 meters is in line with FF. So in this case, it would be FF times those full 20 meters, right? Does that make sense? As I go down this rolly hill, what about that? The force of friction would be here, and then here, and then here. It's always parallel to the surface. So what's the total distance that FF was in the same direction as my distance covered? All 30 meters. All 30 meters. So, friction did more work in which scenario? Bottom one, right? So friction is therefore a path-dependent force. It mattered. It didn't just matter how far down I went. It mattered how I got there. Friction matters how you get there. That's why it is path-dependent. It is not a conservative force. Another example, if I do this, gravity is going to be the only thing acting on it. I toss it up and I catch it, right? It came down with the exact same amount of kinetic energy that it started with. Now, if I roll this, not roll, but push, if I push it across, it ended up here, right? I'm going to get it back to where it started. To do that, because there's probably no energy stored in it, and if there is, it's not just going to spontaneously go over there. That would be a witch or a ghost. If I push it though, right? Did it end with the same kinetic energy that it started with? Yes or no?
Yeah.
How so? Right after I pushed it, it had kinetic energy because it had a velocity, and now it ended up with none, right? So there was a change in kinetic energy. Friction occurred, and it changed the amount of energy in the system. It did not get to come back with the same energy that it had at the beginning. Even after I did extra work to it, I pushed it both ways. In this scenario, I push it one way, and it still gets back to me with the same energy I put in, okay? Same thing goes with a spring. A spring is going to oscillate back and forth. Let's say that it's a frictionless spring, so it's just going to oscillate back and forth forever and ever and ever and ever, right? If no matter what, at each time it goes through that equilibrium length, we know that its velocity is going to be maximized, right? It's going to have its max velocity when it gets to the middle, because that's where it's going to have the least amount of spring potential energy. At that point, if it's frictionless and it oscillates back and forth and back and forth and back and forth forever and ever and ever and ever, right? Every time it gets back to that location, it's going to have the same amount of kinetic energy. It doesn't matter how many times I oscillate between checks. Like if I check on the very first oscillation, hey, how much kinetic energy does it have in the middle? And then I check 100 oscillations later, same amount. What about 1,000,000 oscillations later? Same amount. It's path independent. It doesn't matter how many times that spring oscillates, it's going to always have the same kinetic energy in the middle that it does at the beginning. And that's why it's path independent. Tension, not so much. If I pull on a string and I pull a box towards me, right? I'm pulling on a string. You might say, why isn't there any energy stored in that tension of the string? Well, when I let go of it, what happens to the string? It drops, right? There's no tension left in the string. I did not apply tension to the string and then the tension held. That didn't happen. The string just dropped. It doesn't have any energy in it. It can't move anything, right? Okay. Questions? Let's do